Oh, okay, great. So, last lecture. Let me just remind you from last time that we were interested in agnostically learning a single half space, F, and the domain was Rn, and for the time being we were thinking about the Gaussian distribution. And if you remember, no matter what the underlying distribution it is, we've seen that it suffices to find a polynomial approximator for the Boolean function that you would like to learn, or the class of Boolean functions you'd like to learn. And that means that with respect to the underlying distribution, again in this case it's the n-variate Gaussian, if we want to learn half spaces agnostically, it suffices to show that you can always find a polynomial approximator. So in L2. So we need to just construct a low degree p such that p minus the sign of w dot x, this is our unknown half space, w is unknown, squared is at most epsilon. And since we're working in Gaussian space, whatever the, let's assume all of the half spaces are origin centered for the moment, just for simplicity. But whatever the optimal half space is out there with respect to your data, you can just rotate everything and assume that the optimal half space is 1, 0, 0, 0, 0, 0, 0. So this reduces this particular problem, which is in Rn, to just a problem on the line with respect to the univariate Gaussian density. And this expectation can be written as this integral. And then, you know, this may look slightly intimidating, but we talked about how once you have an orthogonal family of polynomials with respect to some distribution, then it makes sense to talk about the Fourier polynomial with respect to that orthogonal family of polynomials. So we know, just from kind of basic facts, I'll call it, that the best fitting degree d polynomial for this particular function, sine of x, is the sum from 0 to d of c of I h of ix, where c of I is the Fourier coefficient of the sine function. Okay? So h of I is the ith Hermite polynomial, and c of I is the Fourier coefficient of the sine function. This is the best degree d fitting polynomial. We even know an explicit formula for the CIs. It's sort of easy to see that it's 2 times the integral from 0 to infinity of the ith Hermite polynomial times the Gaussian density. And as I said, the Hermite polynomials are specifically constructed to be orthogonal with respect to this density. So this is actually, this is a very nice quantity to work with. If you look in a book on approximation theory, you'll see this, probably see this term floating around all over the place. And so it wasn't too difficult for us to actually compute what the error of this polynomial is. Again, you have Plancherel's equality. So the error of the polynomial, of this degree d polynomial, is the sum of the squares of the coefficients that you didn't choose. So it's the sum of the squares of, it's sum of ci square from d plus 1 to infinity. And then you just need to estimate this quantity, which I'm sure is well known before we did it, but we did it anyway. And it turns out to be big O of 1 over the square root of d. This means that if you choose d to be big O of 1 over epsilon squared, then this particular integral here will be at most epsilon.
Can I just ask?
Yes.
So you're learning with respect to the Gaussian.
Yes.
And you said, sort of without loss of generality, this half space goes through the origin.
Yes.
But that, so if it shifted away, that's not so without loss of generality anymore, right?
If the threshold is not 0, you're right.
You know, so.
So in this calculation, you can just include a minus theta and be just a little bit more careful, and everything will work out. It's really not a problem. Because you can still assume that it's like the line x equals 1, but the rotational symmetry is fine, but it'll be shifted a little bit. So and you end up shifting something inside the integrand, and it's.
So now you're working with sine of x minus a constant.
No, I understand. I'm just saying these functions are now no longer orthogonal with respect to. I mean the.
No. They're still orthogonal with respect to the line.
The mass, but
right.
It's not.
And that's all that matters, because for any function on the line, Doesn't matter what the function is, as long as it's the Gaussian density, this is still true.
Oh, so you'll get hit in the O of 1 over root d here. I mean, so basically less
Yes.
than mass is near where the action is.
Yes, yes,
Okay.
yeah.
I'm also a little confused.
Okay,
so
good.
You're getting uniform examples, right?
Yes.
And now you find the p that sort of...
No, no, so all I'm proving here is the existence of some p.
Yeah, but
Then
we
the
need to-
algorithm will be polynomial regression. So I'll take a bunch of examples and I'll minimize expectation of p minus y.
And then you have to... The fact that there exists a p that does well doesn't imply that the p you will find here actually does well. Does
But
it?
we proved that 2 days ago, the fact that there exists a p that does well, whatever polynomial that you find, will be almost as good as the one
and
that
this
does
is true
well.
also in the agnostic case?
Yes. Yes. So it always remember we had the when we were doing LMN. No, it's not Occam's razor. When we were doing LMN, we did that almost triangle inequality to show that it was like 8 times op plus epsilon. And so if you can just by kind of direct calculation, you use the triangle inequality. You add and subtract this p that you show that has existed. So the p that you find minus the optimal p is going to be, their expectation is going to be small. And then the optimal p minus the function you're trying to learn is also going to be small by this thing. Right? So no Occam's razor here.
Okay.
I don't have any chocolates.
Yes.
Yeah. You can snack. You can eat one. I give you permission to eat one yourself. Okay, and the last thing I wanted to remind you of, and I don't think. Oh, we might have to come back to integration a little bit later, but the last thing I just wanted to casually mention is the analogy between writing a function as a linear combination of parity functions when your distribution is uniform on the cube, and again, if you're working with a function in Rn, as long as it's square integrable with respect to the Gaussian density in Rn, then it can be written as an infinite sum, or very closely approximated by an infinite sum of products of Hermite polynomials. And you'll have this Plancherel equation. So I'm just trying to really nail home the fact that though, I guess, you know, when we were thinking about learning with respect to Gaussian densities, and when we started thinking about it, we didn't think it had anything to do with learning with respect to the hypercube. You know, because you have this nice discrete Fourier analysis. But then we sort of realized that, you know, more generally, it doesn't matter that, you know, whatever domain that you're working in, as long as there's some family of orthogonal polynomials, you're always going to be able to do this decomposition. And you're always going to have these kind of nice facts that we use in the discrete setting, namely Parsifal's equation and best fitting, you know, degree D polynomials. So that was just sort of very helpful to think about, and I'll come back to this in a bit. Okay. So
Christoph had a slide which said general LCA theorem. He said more or less the same thing. So the whole
yes,
this whole theory extends much more generally.
Yes. Yes. So, and that's why I asked when he was talking about LCA if it corresponded to Gaussian space.
Almost.
Right. So but I feel like kind of the approximation theory perspective here is somehow different from the harmonic analysis setting. I don't know. I feel like the perspective and the techniques are a little different. No, you disagree? Okay.
So one question we're already discussing, I'm just curious. So one of the key discoveries in approximation theory many years ago is that in many of these problems, you can get much better approximation if you allow rational functions rather than polynomials.
Oh yeah. In fact, I've used that to great effect. Yes.
You did?
Yes.
And I wonder, I didn't see this in machine learning.
Oh,
so,
yeah,
so
yeah.
It was
Yeah.
For example, a good example, this I think goes back perhaps late 60s, is in fact the absolute value, what's the sign? The absolute value.
Yeah.
Discussed how often is it to approximate with polynomial, how well you can do if you allow yourself.
Yeah, I've used that fact in I think 3 papers. The only issue with rational functions, I love rational functions. The only issue with rational functions is that when you want to find the best fitting degree D polynomial, there's this L1 polynomial regression algorithm. You can find it. Finding like a low degree rational function that minimizes something is a non-convex optimization problem, and it's horrible. It's algorithmically difficult to deal with. That's for another mini course. Okay. So, yeah.
In what you have shown, there is one thing that is actually very specific to Hermite polynomials and Gaussian, namely this tail bound that O of 1 over square root D, right?
Yes.
That's a delicate point.
Yes. Yes.
If you switch to a different measure and different sequence of orthonormal polynomials, you get in trouble because usually you don't have as nice.
Yeah, exactly. So,
nice bounds there.
So, for example, one other thing that we looked at was if the distribution on the line was log concave instead of Gaussian, and then your tail becomes something like e to the minus t rather than e to the minus t squared. And then actually figuring out what this bound is, we couldn't even quantitatively come up with a bound. We knew by compactness that there was some bound that depended only on epsilon, and it was some function of epsilon, and we left it that way. And then later we found a survey that says you actually need to choose d to be like 2 to the 1 over epsilon squared. So it's... anyway, if you were here 2 weeks ago for the talk that I gave on moment matching polynomials, then that was another way of trying to get at these quantitative bounds without having to go through all of this machinery and handle the log concave setting, which seems to be difficult. Okay, so just looking ahead for a second, let's say we wanted to learn f is the sine of w dot x minus theta and the sine of v dot x minus theta. So it's theta 1, theta 2. So it's the intersection of two half spaces. I don't know how to get this machinery to work for such a function. I don't know how to. You can't project it to one dimension anymore, and I don't know how to do the integration. And so, sort of, we talked to a lot of people who are good at integration, and they also could not tell us how to handle this case. Like I said, they were more interested in cylinders in 3 dimensions and their conic sections. Then they thought maybe they could do something. But so what I want to show you is a different proof of this fact that there exists a low degree polynomial approximator for the sine function. And this proof will generalize very simply to more interesting classes of convex sets and actually lead to a bound on all convex sets. Okay, to do that, I need to define something called the noise stability of a Boolean function. So how many people in here are familiar with the noise stability of a Boolean function? Okay. Not everyone, so good. I will definitely define it then. So first let me define it for the cube. This is the probability when you choose x. And then I think I weirdly use z. Z is an epsilon perturbed version of x. So you choose x at random, and then for each bit independently of x, you flip it with probability epsilon. And then you're interested in the quantity, what's the probability that f of x does not equal f of z? Okay. And there's also the Gauss. We can also define, since we're talking about Gaussian distributions, and I want to sort of cover both cases, uniform over the cube and Gaussian, we can also define the Gaussian noise stability of f. How many people have seen the Gaussian noise stability of f? Okay, slightly fewer. So this is the again, we'll fix, maybe I'll write g. This is the probability when you choose x according to the n-variate Gaussian. And then y according to an n-variate Gaussian. And I'm going to set z to be 1 minus epsilon times x plus square root of 2 epsilon minus epsilon squared y. And I'm going to look at f of x, sorry, g of x does not equal g of z. It's the same idea. I'm going to pick a random Gaussian point. I'm going to perturb that Gaussian point by some other much smaller in magnitude Gaussian. I'm going to add up these points, and I'm going to look at the probability that g of x does not equal g of z. So in both cases, I want you to think about this quantity as sort of, well, what's the probability that when I randomly choose a point and then I perturb myself a little bit, that I end up on the other side of the half space? And in both cases, I want you to think about these quantities, looking ahead, as some type of surface area. If your set has a very large boundary, then that should somehow correspond to these being large. Okay. So why are we looking at these? Everybody okay? For the people who haven't seen, everybody okay with these quantities? Okay. So claim is that, and we can quantify this in a second, but low noise stability implies low degree polynomial approximators. So what's the relationship between the noise stability of a function and a polynomial approximator for that function? So I want to show that if, the relationship between kind of the coefficients of a of a function f and its noise stability. This is 1/2 minus 1/2 expectation of f of x times f of z. And then I think Johan has done this twice now, but maybe this is just slightly different. We can look at the Fourier expansion of these functions. I'll kind of skip some steps because I think we've seen this before, but when you multiply all of these out, all of the terms where s does not equal t are going to be 0, and you're going to be left with terms where s equals t.
You forgot to write the sigma sign, the sign.
Oh, yeah.
The sum sign.
Yeah.
No, before outside, because you have
Outside of S.
Oh,
outside
yeah.
of F.
Right. Thanks. Let me just write, this is little x times s, and this is little z times s. So this is the parity of the bits in x times the parity of the bits according to s and z. And an individual bit is 1 minus 2 epsilon. It's the expectation of just x1 times z1 or xi times zi. So this is And then, right. So, okay, so you can see some relationship now between the noise stability of f and its Fourier coefficients. And the bottom line is that sum S is at most some constant times the noise stability of f. So the Fourier spectrum, or the Fourier mass of coefficients on degree greater than 1 over epsilon is some constant bounded by the noise stability of epsilon of f. You can see this by, you can multiply the left and right hand sides by 2. Then you'll get 1 minus something. 1 is equal to the sum of the squares of all the Fourier coefficients. Pull some things out. It's not too difficult. And then the upshot is that, so if the noise stability of f is some, let's call it h of epsilon, then I always write this wrong. Then if then the sum of the squares f hat of s squared is at most epsilon, where k here is 1 over the inverse function of epsilon. Okay, so it's not really important if you totally understand this. I mean, just the high-level idea is that, you know, if you want to get a good bound on, if you want to understand how well the sum of the squares of the Fourier coefficients are concentrated, it suffices to get some bound on the noise stability. And what we're going to prove is that the noise stability of a half space is order square root of epsilon. So the inverse function is going to be epsilon squared, and that means we'll have to choose k to be 1 over epsilon squared. And that means that if, you know, the sum of the squares of all the coefficients beyond level 1 over epsilon squared are bounded by epsilon, and that will also imply that we have a Fourier polynomial of degree at most 1 over epsilon squared that approximates our half space, if we can prove this bound on the noise stability of the linear threshold function. Okay, and the roughly the same thing is true if instead of writing noise stability at epsilon of f here, I had put Gaussian noise stability of epsilon of f. You would also get the same type of concentration, but instead of you know, Fourier coefficient, the Fourier polynomial over the cube, you'd get Fourier coefficients corresponding to the Hermite polynomials. Okay, so you get exactly the same thing. So one nice thing is that, so everybody okay with the relationship between noise stability and approximation by a low degree polynomial?
The Gaussian case, instead of the size of S, what do you get? You get the sum of squares? Or?
Instead of the size of S,
They're integers now, right?
you can still measure the size. It's an index set, so you can still measure the size. S will be an element of a tuple of natural numbers. So it'll just be the sum of the elements in that tuple. Okay, and the nice thing, so now that we have this relationship, what is the Gaussian noise? The Gaussian noise stability of you know, so the Gaussian noise stability of a half space. So this is sine of x does not equal sine of z. You could imagine in the plane choosing a bivariate Gaussian where x and z are 1 minus epsilon correlated Gaussians. Then you're interested in what's, so I choose a bivariate Gaussian where x and z are 1 minus epsilon correlated. And I want to know what's the probability mass of this region. This is where the sine of x does not equal the sine of z. This is also the region where sine of x does not equal sine of z. And this is a classical, this is a classical thing in probability. It's 1 over pi times the arc cosine of 1 minus epsilon. This is approximately square root of epsilon. So you'll get that immediately the Gaussian noise stability of a half space is at most square root of epsilon. By this relationship, that implies that there's a degree 1 over epsilon squared polynomial, Hermite polynomial that approximates the half space. And so that recovers, you know, this proof that we did that kind of looked at the integrals of Hermite polynomials. You sort of, this falls out immediately. And another nice thing is that we can apply the following trivial observation that the Gaussian noise sensitivity of f and g is at most the Gaussian noise sensitivity of f plus the Gaussian noise sensitivity of g. That is to that's just to say, imagine I have the intersection of two half spaces. And I want to know what's the probability when I choose a random point and I perturb it that it flips into this region. Well, that's certainly at most the probability that it flips into this region, or the probability that it, the probability that it flips over this hyperplane, or the probability that it flips over this hyperplane. So it's just a union bound. So you get this immediately. And this implies that the Gaussian noise sensitivity of the and, actually it's any function of k half spaces is at most k times the square root of epsilon. And this will translate into an n to the order k squared over epsilon squared SIME algorithm for agnostically learning any function of k half spaces. So this was this is nice. I mean, we came up with this quantity, Gaussian noise stability. It's easy to see why it corresponds to polynomial approximation. It's very well known that there's a very well known formula for a single half space. And if you want to generalize this to intersections of half spaces, it's very, very simple. You apply a union bound. So it's great. Now you can see if you wanted to choose k to be very large, this bound will start to become uninteresting very quickly. So we'll have to talk about that in a second. But I wanted to prove to you that I wanted to move back to the Boolean domain and prove to you that the Boolean noise stability of f is at most square root of epsilon. Okay. I mean, I sort of just said, oh, well, it's classical in the Gaussian case, but for the Boolean case, it's more delicate. It's certainly not classical. So the noise stability at f being order square root of epsilon, the first there's a very slick proof due to Perez for this fact. And I think actually there was a weaker bound in Ben-Yamini Kalai Shram. Is that right? Maybe it wasn't. Maybe it was epsilon to the 1/4 instead of square root of epsilon.
No.
I forget. Something like that. Okay. And then so Parikshit Gopalan came up with a simpler proof. So it's not a very difficult proof, but it's sort of tricky to teach. He had a simpler proof, and then there's a proof that's in Diakonikolas, Raghavendra, Servideo, and Tan. It's a paper on the Gaussian lineal conjecture that I'm going to show you that I think is even simpler. Have people seen this proof before? Or? No? Okay, I know you've seen it. So let me show you the proof. It's slick. It's very slick.
So which of the different proofs are you showing us?
What?
Which of the different proofs? Or you have to
The
know-
easiest one.
The easiest.
I'm going to show you this one. I mean, the annoying thing, the nice thing in the Gaussian case was that we could sort of just assume that the half space is sine of x. I mean, it's really, really simple. And over the cube, you have these annoying integer coefficients that are hard to reason about. So, f is sine of. I really want to do this right, because it's really slick. So, I need to define the influence of a Boolean function. This is from I think most people have seen this. This is this is a super important quantity in the analysis of Boolean functions, it's introduced by Benor and Lineal. So this is the probability that when I choose a random x, and I flip the ith bit of x, that the function changes sign. And the sum of all the influences, I'm calling the average sensitivity of f. And I guess the one fact that I'll need is that the average sensitivity of f, where f is a monotone function, is at most, and f is on n variables, is at most square root of n. Okay. Would you consider this a homework exercise, or?
You can assign it to someone who likes homework.
Okay.
Give it to him.
I'll just say that if you haven't seen this before, that if f is a monotone function, then the ith Fourier coefficient, so the expectation of f times xi, this is the ith Fourier coefficient, is exactly equal to the ith influence of f. And since the sum of the squares of all the Fourier coefficients is at most 1, then the sum of the first n Fourier coefficients can be at most root n. So this is just the key idea to showing this. It's not difficult. Okay, so I guess what I'm going to show you is that noise stability is actually very, very related to average sensitivity. And for a while, it sort of seemed like these were fundamentally different quantities, but now I feel that the best way to bound the noise stability of a Boolean function is really to just try and understand what its average sensitivity is.
And the fact that it's a limit is obvious. You let epsilon go to 0. And,
Yes.
And
Yes.
epsilon roughly being 1 over n.
Correct. Okay, so what I'm going to do so remember, we're interested in the probability that when z is a perturbed version of x, that f of x does not equal f of z. Okay, now, so, you know, x and z have some joint distribution. And I described it by first choosing x at random and then flipping each bit of x with probability independently with probability epsilon. So instead, I want to do the following random experiment that will result in the same joint distribution. First, pick x at random again. Then pick a random partition of n into m sets. And m here is going to be 1 over epsilon. So pick x at random. Pick a random partition of n. Then pick R, so pick one of these sets, S at random, and flip all the bits in S sub R. Okay, so all I'm saying is, instead of independently flipping each bit with probability epsilon, randomly partition the bits of X into these buckets, then pick a random bucket, and then flip all the bits in that random bucket. Okay. You're going to get the same distribution. So right, so just so I don't do this wrong. So alpha is going to be partition, and now z is going to be a random. This is going to correspond to, well, you'll see in a second. Then I'm going to set let me say this. This is y.
Sorry, is this immediate? That if you pick a uniformly random partition and then pick a random set, it'll be it's the same distribution as picking.
Yeah. Well, think about it for a minute, and you'll convince yourself it's the same. Then I'm going to set xi to be ai times z of alpha I, or sorry, y sub alpha I. And I'm going to set zi to be ai times y sub alpha I with the rth bit flipped. And I want to claim that the noise stability at epsilon of f is equal to the probability that I choose A at random. Sorry, I forgot the most important thing. So I'm going to choose A at random, alpha at random, z at random, r at random, that f of x, f of x does not equal f of z. So I'm claiming that this is like your input string. So this is some random string A. Then I'm going to pick a partitioning into buckets. I'm going to pick y. And I'm going to take ai times y alpha I. So this is literally picking a random string of length n. And then I'm randomly flipping some of the other bits. So it's OK. I mean, x here is still uniformly distributed over minus 1 to the n. And z is going to be the same as x, but one bucket is going to have its bits flipped. Okay, so these distributions really are the same as just a random x and a perturbation. You know, I mean, we're introducing these new kind of fake variables that tell you which bits to flip. Everybody okay with this so far? Maybe you see how to do it already. So this is just the probability, again, over A, alpha, y, and r, that f of A, alpha, y is not equal f of A, alpha, no, I meant x here.
But f of x not equal to f of z. Adam, this is what you wrote there.
Yeah.
F of a alpha y is
f of a alpha y is not equal to f of a alpha y.
Yeah, that's what I mean. Thank you. Right. And then this, I'm doing nothing here now. Just writing things in terms of an expectation of an indicator function. And then I'm going to pull in my choice of r. R could be one of m things. I'll explain this in a second. So this is the indicator function that somehow, like, this is very simple. This is a very simple idea, and somehow it's like tricky to just like precisely write down. But now you can see that. So think about. You know, for a fixed setting, of A and alpha. So for a fixed setting of A and alpha, I have these new variables, the yi's, but there are only m of them. And so for every fixed setting of A and alpha, the function is still a half space. But it's a half space in just m variables. So I guess the way to think about it is
I think the way of thinking about it is that it's just simply reducing the original problem to the problem of having a cube and you have a half space and you are just flipping one bit. And so
well, I'm trying to
noise sensitivity with epsilon, you are just looking at the noise sensitivity with respect to just changing one coordinate of x.
Yeah, well,
I'm trying to. Which is well known that it's square root of
m.
Of m.
Right. So I'm trying to reduce it to that. I didn't.
Well, you have already reduced.
Okay, so I don't feel like I did a good job explaining it, but. I guess the idea is, you know, you're now flipping just all of the variables in one bucket, but you're flipping just one bucket now where the variables have been partitioned, and you know, each bucket has sort of one variable associated with it. So flipping one bucket corresponds to flipping just one variable, and if you're flipping one variable, that's just the influence of a half space, which is a monotone function. And so this is going to be 1 over m times, this is the sum of the influences of a half space, which is a monotone function, which is at most root m. And so this quantity is 1 over the square root of m.
Does it mean that this reasoning works not only for the sine function, but also for any monotone function?
No, so the subtlety here is that for any fixing of a and alpha, the function must still be a half space or a monotone function. So it has to be, in here it has to be a half space. So it requires some very weak closure property.
Does this argument show that the unit weights function is the most noise stable?
Majority.
Well, majority is the
It's
most.
the least, the least noise stable among all the half spaces.
I don't think this argument shows it.
So actually,
I think direct calculation of just.
It's no.
I thought it was majority.
What?
I thought majority was.
The least noise stable?
Yeah. No, majority is the most noise stable.
No. Majority
Wait,
is
which
the
you-
least, the least
the-
noise
you
stable
want the
among
least-
all the weighted majority.
Yeah, it's the least noise stable.
Hold on.
Because the most noise stable is the constant function.
The dictator.
Okay. Yes.
Data.
Yeah, you're right.
But maybe this type of argument may show it. Or...
But can I draw a picture like how I see this?
Yeah. Come on up. Draw a picture.
Because so the way how I am seeing this is that so here is like an original cube, which is kind of, I'm just drawing a funny picture. But then you have the A, and then so you have this partition. And so this partition, like if you are looking at like all possible 2 to the n ways of, 2 to the m ways of partitioning it, well, then that would give you like a little, like 2 to the m points here, kind of like a subcube. It's kind of like a parallelepiped subcube inside the cube. And so you have the original threshold function, which is still, so now I'm just focusing on these, and now I'm averaging over all these pictures. So on these, all what I have to see is that just how many edges it cuts. And so it's well known that the fraction of the edges, so inside this small cube, which is just again the like sort of, so it's created from this fixed A, like those. So the number of edges it cuts is just square root of m fraction. And so when you are averaging it out over all these kind of patterns, then that you just get the same ratio.
So one more thing here, this says that
Thanks.
we understand, I'm just trying to interpret what Mara just said. We understand very well what happens when you change only a single bit.
Right.
In here, with noise sensitivity, we have to understand what happens as we change epsilon n of the bits.
Correct.
And his argument says that if you restrict it to you are coming back to this situation.
Right.
I can't claim that I see all the details at once, but the concept is very clear.
Okay, good. The way I think about it is, instead of sum of wi xi, you end up making these new variables. I mean, sort of just repeating what you said, but you have, z alpha I. So now, instead of randomly choosing xi's, you could randomly choose xi z alpha I. It's still a random input. And then instead of flipping an epsilon m of these xi's, you could just flip one of these z alpha i's, and that's going to end up flipping epsilon m of the variables. And so it's just what's the influence of this function when you just flip one of these nu z
So
So when we
outside.
get down to this smaller cube, it's a dictator function or an arbitrary threshold?
It's a linear threshold. It's an arbitrary linear threshold function. But now you're just right. You're just interested in what's the influence. What's the
Oh, I see. We're just
what's
looking
the
at of
influence?
that
How many
and we
items are
and we know that that's the total influence is root m on m variant. So
And it's uniformly chosen among the coordinates of z. with
right,
which one-
right, exactly. Yeah. So it's adding like a ghosting variable here. Right. Okay, maybe when I do this at 1:30, I'll say that better. Okay. Oh, good. I still have some time.
Can I make a comment about something that you said before?
Yeah,
When
sure.
You spoke about this wedge, the intersection of two half spaces and so on.
Yeah.
Something that occurred to me is that then you said I'm applying just union bound, and all I care is just how many inequalities define this, let's say, polytope.
Right.
This somehow rings. So there was, for example, just here there was a lecture of James Lee. There is this whole concept, the Yanakakis proof of the hardness of traveling salesman. You can't do it well.
Right.
And then the whole concept is you have some polytope, but somehow you prefer, if possible, to lift it to a higher dimension. If
Right.
this polytope in higher dimension is determined by has fewer facets.
Right.
There seems to be some
Relationship
possible
here?
connection between the two. I wonder if there is anything to it. Because, right, I mean, the complexity of what you pay here depends only on the number of defining facets.
Correct.
So I wonder if the two things somehow
Right.
come together.
I'll think about it. Okay. I'll just say that this argument, once you have a bound on the noise stability of a single half space, again, you can use a union bound to get bounds on the noise stability of functions of half spaces over the cube. Just, again, by applying a union bound, and you can get more results. You can get similar results for the Gaussian case as over the cube. Okay, but we wanted to do, oh good, I still have time. So we wanted to consider the case, we wanted to learn yet more interesting convex sets. So we didn't want to restrict ourselves to wedges. We wanted to fix K an arbitrary convex set. And we were interested in, can you find a polynomial P? So I'll say K of X is +1 when X is in the convex set, and -1 when X is not in the convex set. And then I was interested in, we were interested in, again, can you find a P such that expectation of P minus K of X squared is less than epsilon. This expectation, let's say, is with respect to the Gaussian. And we know now it suffices to bound the Gaussian noise stability of K. So maybe we could get a good bound on the Gaussian noise stability of K. But if K is an arbitrary convex set, it could be the intersection of potentially infinitely many hyperplanes or half spaces. And so the bounds that we get here are uninteresting. Now, earlier in the lecture, I said you should think about noise stability, or the Gaussian noise stability, roughly as some notion of surface area. And that leads me to the definition of Gaussian surface area. Because instead of analyzing the Gaussian noise stability of a convex set, the characteristic function of a convex set, we're going to reduce Gaussian noise stability to bounding Gaussian surface area. And then we'll be able to make use of some results on Gaussian surface area of various convex sets. So what is Gaussian surface area? Let's just start with what is surface area. The usual notion of surface area. This is the limit, let's say is delta goes to 0. So the surface area of a set K is the limit, for any set K, is the limit of the volume of a delta blown up version of K minus the volume of K divided by delta. So you can take...
Delta divided by dimension.
No.
So,
So K sup delta here is you take every point in K and you put a tiny ball of radius delta around it. You look at its volume. You subtract off the volume of the original convex set, K, and you divide by delta. And Gaussian surface area is just going to be the same definition, except replace volume with probability mass. So it'll be the probability mass of some set, in Rn weighted according to the n-variate Gaussian density. So by volume, I really mean probability mass. So that's the definition of surface area. There's also, if your set is sufficiently smooth, you can define it as a surface integral you integrate along the surface of your convex set the Gaussian measure with respect to some surface measure. I don't know if this, but you can think about, so for example, if you wanted to calculate the Gaussian surface area of a half space, let's say of the half space x equals 0. So here's your half space.
One.
No, x equals 0. It's everything on.
Ah, okay. In what dimension?
We're in, say, n dimensions.
So this is x1. First coordinate, right?
Yeah, first coordinate. Okay. But I'm saying the border of this half space is the line x equals 0. Then you can integrate the Gaussian along this, just integrate the Gaussian measure along this line, and you'll get that the Gaussian surface area of a half space is a constant. In fact, it's 1 over root 2 pi.
So what is K
Rather
delta?
than integrating, it's easier to see with the formula, right?
Oh, yes, or you can use this formula. Yes,
Because-
and then you'll take the derivative of the CDF.
Yeah, and just the one-dimensional CDF. So then
Yes, exactly. And you'll have, and its maximum point is when the PDF is at 0. Yeah. What was the question?
What is K delta? Is the delta environment of,
Yeah.
Yes.
Involved with the
but then why don't you divide it by 2 delta? Because like if I am taking a plane or some
Because
thing,
it's
then I have
actually
delta
going-
in this direction and delta in that
No,
direction.
but that direction is already there in the body.
Yeah.
Also, it's just
Inside,
the outside.
Just the
Yeah.
outside.
Yes. You're taking like a shell around. The set.
So it's just the
Inflate
outside.
You're taking like little shells around the set, and you're looking at its volume as it gets smaller and smaller. And just to contrast this with normal surface area, if
what happens if you have a manifold? Then you have this issue of a factor.
I'm not prepared to
It's
answer
not
that.
a
I'm not,
body.
I'm not prepared to answer that question.
So he's looking at
This
bodies.
only makes sense if the body is full dimension.
Yeah. These are convex or not necessarily convex. but-
It's the issue if you have a manifold, then take all the points with
Wait, I don't want to get sidetracked on this because I'm running out of time. So,
Sorry.
okay. So if you have if you're looking at the surface of a sphere, as the radius gets larger and larger, it has more and more surface area, traditional surface area. but its Gaussian surface area is getting smaller and smaller because the boundary of the sphere is getting farther and farther into the tail of the Gaussian. And you can bound the Gaussian surface area of spheres. It turns out that the sphere of maximal Gaussian surface area is not the one centered at the origin. It's slightly offset because you want sort of as much of the surface of the sphere near the origin of the Gaussian as possible. And these calculations are a little delicate, but they're doable. Okay. And what's interesting about the main fact that we use about Gaussian surface area, and it's implicit in the works of Ledoux and Bézier, is that the Gaussian noise sensitivity of a function is at most root pi times root epsilon times the Gaussian surface area of f. Not totally surprising, but
With this you mean the plus one set, f is Boolean?
yeah, I'm abusing notation here. So f is the characteristic function of, maybe I should just write k. And I said that k was the characteristic function of the convex set.
There is also inequality from the other side?
Oh, that's more subtle. That's not always true. That's a more complicated question. It's not clear. So then, once you have this relationship, you can really start, doing some good literature searches. So it turns out that Keith Ball and also Fedya Nazarov proved that for any convex set, set K, the Gaussian surface area of K is at most n to the 1/4. And so, when you move from Gaussian surface area to Gaussian noise stability and then back to a polynomial approximation and then to the learning result, this will imply that you can agnostically learn any convex set in time n to the square root of n. Okay, so you'll actually get something, a non-trivial learning algorithm for any convex set.
This n to the 1/4 is best possible?
Yes.
What depends?
You look at a sphere of a sufficiently large radius, and you look at an exponential number of random tangent hyperplanes to the sphere.
What's the body?
Well, the body is the intersection of these randomly tangent hyperplanes to the sphere.
So it's a polytope that you get by somehow bounding the sphere with lots of tangent hyperplanes.
Yes. Yeah. And then also there's a result due to Nazarov that says that this is very interesting, that if you have the intersection of K half spaces, the Gaussian surface area is at most square root of log K. Well, some constant times square root of log K. So this is, remember when we were using the union bound to sort of bound the Gaussian noise sensitivity of an intersection of K half spaces, you got something that depended on K. If you use this fact about Gaussian surface area, you get something that depends on root log K. it's very interesting, to me at least, that it's a statement about sort of the probability that you lie within some boundary of the intersection of k hyperplanes, and that when you choose a random point, that you lie within the boundary of the intersection of k hyperplanes, and it doesn't at all. I mean, has a much better dependence on k than has a much improved dependence on k. So it's a very interesting fact.
In view of what you said here, it would stand to reason that perhaps the answer there should be fourth root of log k, right?
Why?
Because here he said it's an exponential number of hyperplanes or half spaces.
Yeah, it is an exponential in the fourth. Yeah.
Then if I just want to interpolate between these two, I would guess that the answer there perhaps will, or do they know that this is type?
This?
That should be perhaps fourth root, just to make it
No,
consistent.
no, this is a type.
That's type.
Yeah. For example, for the cube, it's attained by the cube, the solid cube. And so I guess, what I didn't state, I should say more generally. If S is a bound on your Gaussian surface area, then you can agnostically learn the concept class in time n to the order s squared. I should also point out that in the Boolean case, so if f is an and of k half spaces, and we're working over the cube, so there is a notion of Boolean surface area, but I haven't found it to be useful in any sense. But Daniel Kane just proved, like last month, I think, that the noise stability of an intersection of k half spaces is at most some constant times root log k times square root of epsilon. So he also managed to get this bound, and the proof is like 3 pages of elementary calculations. Which is really annoying because I worked on it for a long time. But not surprisingly, these bounds match up.
So Kane's result implies Nazarov's result, I guess.
It will imply the learning result in Gaussian space. I don't know if it'll imply that the Gaussian surface area is root log k.
But can you do these transfers with these, these usual
Invariance principles?
Invariance?
Yeah, you can, yeah. Yes, you can.
And this is how he is doing that?
No. If you want to transfer this, if you want to say, oh, well, since the Gaussian noise stability is something like root log k, and then I'm going to apply an invariance principle and hope that that's true on the cube, it only works for functions on the cube that are sufficiently regular. It's not going to work for all half spaces on the cube. So that's one issue. And also I don't consider the applications of the invariance principle elementary. So, he uses convexity of functions. It's pretty slick. Okay. So I guess the last thing I'll have time to talk about, but I'm glad
Can
that
I ask you one more question?
Yeah.
So, what about learning in the sense that, let's say there is a convex body.
you get uniformly random points from within the convex body.
So points that are sufficiently within the body, I want to recognize them. Points that are sufficiently away from the body, I want to recognize them. And in between.
So you have a margin.
Right. Has this been looked into?
Yes. You can do something. I mean, what you want to do there, depending on what the margin is first apply a random projection into a lower dimensional space, and then We can talk about it later. You can do things. Yeah. Okay, so I wanted to kind of combine all of these ideas and with the result of Santosh for learning convex sets. Actually, I should say, intersections of K half spaces. And this result of Santosh's will not work in the agnostic setting, so there's no noise. But the idea is the following. Let's just look at a wedge again, so the intersection of two half spaces. So we're in Rn, but we're trying to learn the intersection of just two half spaces. So here are the normals, the half spaces. Now, if you could somehow identify a subspace spanned by the normals, so if you could identify the two-dimensional space, which is the space spanned by the normals, then what could you do? I mean, what's the first thing you would do in this learning problem? You would take all of your examples, you would project them into this two-dimensional space, and now I'm in R2. So once I'm in R2, there are lots of things I could do. I could use brute force search, or you could apply our algorithms, and instead of an n here, you could replace it with 2, or whatever dimension that you've projected down to. Okay, so it's, identifying the subspace that's spanned by these normals is it'd be fantastic if you could do that. I mean, it really simplifies the problem. And here's an idea as to why you should be able to identify the subspace spanned by the normals. Okay. Again, I'll think of a wedge. Okay. So remember, we're in Rn, but we're trying to learn the intersection of two half spaces. Okay. So consider, we're getting all of these points. They're drawn from a Gaussian distribution. And let's just look at the positively labeled points. So some are labeled negative, some are labeled positive. Just draw a lot of them and just look at the positively labeled points. In a direction that's irrelevant, namely one that sort of goes through the whiteboard and out this way, what is the variance of all of the positive points in this irrelevant direction? Same as the normal. It's 1. I mean, because in an irrelevant direction, I mean, you just have a Gaussian density here. It's not at all bounded by any of these hyperplanes. But if you look at a direction that's relevant, then what you might hope is that the variance in a direction that's relevant of the positive points is bounded away from 1. So this is a conjecture that we had, that for every direction, for every relevant direction, W, the expectation of W dot x squared is bounded away from 1.
Is it clear that it's less than 1?
What?
Is it clear that it's less than 1?
Oh, yeah, good question, actually. It's intuitively, it seems like it should be the case, I think. But when you actually sit down and try and prove it, it's quite hard. And that's what I'm going to talk about in a second. But it is true that for directions that are relevant, when you restrict the Gaussian in that direction, that the variance does decrease.
It's because it's convex, or?
Well, let me get to it. You'll be excited by the theorem I'm going to tell you. So the conjecture is that for every direction, this is bounded away from 1. And in fact, this is bounded away from 1 by a noticeable amount that you can detect by random sampling. Okay? So let's assume this is true. Then let's assume the conjecture is true. How do we identify the relevant subspace? Sorry?
Take an SVD.
Yeah, I like to call it PCA, but you take all of your positive points and center them. And then if you compute all of the eigenvectors and the eigenvalues, the largest eigenvalues will correspond to eigenvectors of maximal variance, and the smallest eigenvalues will correspond to directions of smallest variance. Okay, so this is, we can apply SVD, PCA to the covariance matrix. I guess if you haven't seen this before, if you pick a direction U and you look at U transpose sigma U, where sigma is the covariance matrix, this is going to be the variance in direction U. And sigma is symmetric to covariance matrix, so the largest eigenvalue and eigenvector will correspond to the direction of maximal variance. So that's why computing the eigenvectors and corresponding eigenvalues will tell you what the largest, what the directions of maximal variance are. And then so after you've computed all of these eigenvectors, you can look at the ones that are bounded away, whose eigenvalues are bounded away from 1. And those are going to precisely correspond to the directions that are relevant. And then you can just work in that subspace spanned by those relevant directions. Okay. So Santosh proved this conjecture is true. And I don't know why we couldn't prove it was true, but I do know why we couldn't prove it was true. We were trying to prove something stronger. But I told this conjecture, like offhanded, after Santosh proved it was true and wrote his paper, I offhandedly told this conjecture to Raghu and Mecca, and in like 5 hours he had sent me like a reference that completely proved the conjecture. So he wasn't there when I needed him, but I will show you the theorem that he found. And it's a theorem due to Caffarelli. And it's a generalization of one of the Braskamp Lieb inequalities. And Mario, this is going to be exactly what you were asking. Okay, so I'm going to let nu be the uniform distribution over a convex set, over any convex set. So you can think of sampling a bunch of positive examples, and that distribution corresponds to nu. And phi, again, will be the n-variate Gaussian. And I'm assuming that the mean, like everything's centered around the origin, or the mean of all of your points is, the mean of all of your distributions here is 0. Okay. So what Caffarelli proved is that for all...
For both phi and nu?
No, yeah. I mean, the Gaussian is going to be the standard n-variate Gaussian, and nu is going to be centered. And so what Caffarelli proved is that for all convex functions psi, the expectation with respect to nu of psi, sorry, I guess I should say, and for all w, Rn, the expectation of psi of w dot let's say y is drawn from nu, is at most the expectation with respect to the Gaussian of w dot x. And this is really inner product here. So, for example, if you choose psi to be the function psi of z to be the function z squared, then you'll get that the variance in any direction when you the variance of any direction of your positive points is at most the variance in that direction of the Gaussian, which is something we sort of already knew. I mean, it's at most 1. Does the statement of this theorem make sense? Or?
Not quite, no.
So you have one distribution, and it's just uniformly chosen points according to the convex body. So that's like you take your set of random examples labeled positive. This is a sample from that distribution. No.
So you take the Gaussian distribution and you normalize it so that the total measure of the body is 1.
So you have the Gaussian distribution. You're getting randomly labeled. You're getting examples drawn from the Gaussian. Some are labeled negative. Some are labeled positive. The positive ones induce a uniform distribution. Induce a distribution over this convex body.
This is the Gaussian measure restricted to
This
the
is the
convex
Gaussian
body
measure
and renormalized.
Right, restricted to the convex body and then renormalized.
And you need to be centered around the origin?
I don't, no.
So what you
Why
didn't-
can't it just be?
anything, any set?
Yes.
Anywhere. You said something about...
Yeah, there's another term here that I didn't want to write, so it becomes 0 when things are centered. So.
Could we get the full inequality? No.
Yeah, it's... minus...
Or you could just define you would just want the convex set to
You
contain
just
0.
subtract off the mean of the distribution.
Oh, okay.
He wants the center of mass.
Yeah, you subtract off the center of mass.
Okay.
So does it make sense that it means uniform and the body is not convex?
Sorry, it's...
Oh, okay. Normalize it.
So it's the same Gaussian centered at the origin, now just
restricted
restricted
to
and
points
rescaled.
within, rescaled to within points of the convex body. Yeah.
So what stops you from sort of being in the direction where W is very large and I don't, it's something normal.
What stops?
I can make U tiny. It's a point.
What's U?
Me.
The body.
Of the body, whatever.
Of the
That's
body.
not U. I don't know.
Okay.
It's all located somewhere where, and you've rescaled,
No,
so
but
it's
you're assuming that
renormalized.
the centroid of this body is at the origin.
Oh, that's not written anywhere.
I said it. Sorry.
Rashi Ban.
So, okay, again. So what's the center of a convex body? So just the center of
Centroid.
gravity?
Yeah, the center of mass,
According to the Gaussian distribution.
according to the Gaussian distribution. Yeah.
All right.
Yeah. Sorry. That's what this... I guess I should have written this annoying term, but... Okay, so let's say that every bounding hyperplane every bounding hyperplane is at distance at most b from the origin. Okay, I can assume this because if if the bounding hyperplane, I mean, we can assume that B is something like square root of log n. If the bounding hyperplane is like very far from the origin, then you might as well just assume that it's not there. And then I'm going to define this function. So the question is how to apply this contraction inequality.
Sorry,
Yeah.
Can I ask why this is reasonable? So if I take, just as you say, the z squared, but sort of, in the direction of w. So if I take my body, I'm sorry, to be stretched out exactly in the direction of w, rescaling the Gaussian is going to give me, relatively speaking, a lot more variance in that direction than just the nice fat Gaussian, the unrestricted Gaussian. So when you say,
Can you ask your question again?
I'm saying it seems unreasonable. So if I let my set, whatever it is, be the line, actually, just take the line.
Yeah. Let's just take the line. Let's just look at the real line.
Yeah.
Okay. And now I want to. So the Gaussian has variance 1 on the line, and now I want to look at the Gaussian restricted to some interval on the line.
Well, it was around the origin.
No, this theorem will hold for any interval on the line. I don't need the restriction to be around the origin. There's a term in the theorem here that will take care of that. But I'm claiming that the variance of the Gaussian restricted to this interval is less than 1, even if you're way out in the tail.
But you rescale this to be a probability distribution.
I'm going to rescale it to be a probability distribution, yes. But I'm still claiming that the variance of this probability distribution scaled and renormalized in this interval is less than 1.
Don't you go ahead? It doesn't make sense.
So why are you talking about variance? You have a convex function. How does variance come into the picture?
So I can talk.
Square.
I can.
Size just
I'm sorry.
it's a special case when size is square.
Yeah.
I see.
Okay, let's talk about it
Yeah,
afterwards.
we'll do it later.
Okay. So let me just show you. The whole trick here is what psi you should choose. So you want to choose psi on the interval minus b to b. Psi of z should equal z squared. And then, and then outside minus b to b, when you hit point B here, you want to choose psi instead to be a tangent plane. Okay, and so what I wanted to claim, maybe we can talk more about it afterwards, is that when you choose this psi, on the left-hand side of this equation, you're going to have exactly the variance in direction w of this distribution restricted to the positive examples of the convex set. And on the right-hand side, you're going to have, remember when we were integrating just x squared with respect to the Gaussian, you get 1. But now we're integrating something that x squared dominates. And so when you integrate it, you'll get something like 1 minus e to the minus b squared. You'll get something slightly less than 1. So on the left-hand side, I'm claiming you'll get variance in direction w of your positive sample points. And on the right-hand side, I'm claiming you'll get something noticeably less than 1. And this will be enough to kind of run PCA and identify the relevant variables. Okay. So I'll just stop here, and we can talk about it more afterwards.
We can take questions during the break, but let's give another round of applause for Adam. He was very brave, especially yesterday when he gave his talk twice. So thank you very much.
I'm sure I simply don't understand.
No, I probably don't understand it.
No.